Well, good afternoon, everybody. So today what I'm going to do is we're going to go through just kind of a made-up uh, process where we're heating water. And we're going to talk about whether we should select an RTD or a thermocouple for this process, where it should go in the process to get the best measurement, look at how to protect it either inside the piping and outside. We'll talk about performance of the sensor, and finally we'll wrap up with the price and then kind of the ongoing maintenance and what you can expect for a lifetime out of a sensor in that type of an application. So those are kind of the takeaways from today's presentation, is just whether you want to choose a surface mount or maybe an immersion style sensor, how do we protect it, what kind of performance can you expect, and then what do we do to maintain it over its lifetime. So what we're going to do here is look at this application, which we just kind of made up. It's in a 4-inch pipe. We've got some water moving through it, and we're trying to heat it up. And then we've got some explosive gases present around the outside of the process. We have to take that into consideration. There's not really any vibration going on in the pipe, and that's pretty simple one. And we'll just kind of step through each of these sections and talk about what to do. So I like to divide these up into these categories. So we look at placement, protection, performance, price, and then the service life. So first off, we need to select whether we want to do an immersion style sensor or a surface mount. Now the surface mount is going to be very easy to install. The immersion sensor requires some sort of a hole in the piping. It's a little more involved to install, but you do get a little better, more accurate measurement in most cases. First off, the surface mount, there's several different styles. Typically, they just get strapped to the outside of a pipe, and then they require some sort of insulation to cover them up so that you minimize the effects of the ambient conditions on that sensor. For example, if we had a process that was running real hot, we would want to, and you've got just room temperature around it. Without insulation, the sensor is going to read lower than the actual surface of that pipe. So we do need that insulation to get the best measurement. Here's a few different styles that I found. They've got this is one we saw just strapped to the pipe, and this, held on with a couple of bolts. And there's just kind of an endless variety of the surface mount styles, and they're all designed for different types of surfaces that require a temperature measurement. Like I said, they're very easy. We're not obstructing the flow, and typically they're very low cost. Some of the negative aspects of them, like I said, we need to insulate over the top just to keep the ambient conditions from affecting the measurement. Most of these are kind of odd constructions compared to a typical cylindrical type sensor, so they're difficult to calibrate. You almost have to have like an oil bath or some kind of a liquid bath to be able to calibrate these. And then finally, we're measuring the surface temperature of the pipe or a plate or whatever it might be, rather than the actual fluid inside the pipe or whatever's underneath like if it's a flat plate type application. There are some temperature transmitter probe combinations that have a little algorithm built in that estimate the fluid temperature in a pipe based on what the surface temperature of the pipe is. They seem to work fairly well. They're going to be quite a bit more expensive, and I think the number of fluids that the algorithm works with may be minimal, but that's another option to look at. The other option is to go and immerse the sensor in the fluid, and these typically are going to give you a much better, more accurate measurement. So we've got a couple different styles. This is a threaded in, this is a sanitary fitting, and then a typical immersion style that uses a thermal well with a spring-loaded probe inside. And these come in lots of different lots of different configurations and ratings and things. And we're going to look at one that's going to be appropriate for our application here. So we have a probe that's immersed into the process without a thermal well. So it might just be in our example here, it's a 1/4 inch diameter platinum resistance thermometer. It could be also a thermocouple. With a thermocouple, we're not going to get as good of an accuracy as what you can get with the RTD. If you remember back on our a few slides ago where we were looking for plus or minus 1 degree Fahrenheit accuracy, we're not going to be able to get that with a thermocouple. The initial thermocouple accuracies are actually nearly exceed 1 degree Fahrenheit just right out of the box without having it connected to any kind of a readout display or a chart recorder or whatever. So we kind of dismiss the thermocouple as giving us the accuracy we need for this measurement. And so we're going to be talking mostly about the platinum resistance thermometer today. So, and these are going to give you a fairly fast response with the direct immersion style. Again, fairly low cost, and we can get away with a pretty short immersion length. If we had a really high flow rate in this pipe, durability could be an issue. Certainly maintenance is an issue because we have to shut down the process, drain the piping, and then pull the sensor out and maybe calibrate or replace it, whatever the case may be, and then start the process up again. If we were to add a thermal well into this process, then doing maintenance on the sensor becomes a lot easier because we have the piping is completely sealed up. Provides extra protection for the sensor, a lot of extra strength to it, and I think for our process here, this is going to be the direction we're going to go. Some of the limitations here, though, we do get a slower response time. So if you had a process that was changing temperature rapidly, a thermal well like this would probably not be suitable. Typical response time, or actually I should say a time constant for this, would be around 25 seconds. So if you're, and then that's only for about roughly 2/3 of the total, for it to read the total temperature change. So if your process is changing temperature, you know, let's say every minute it's going up and down, this would be a bad choice. However, in our process here, we don't have that issue. It's just a kind of a steady state measurement where we're heating water. The next section here, we're going to talk about how to protect this sensor. You know, we've got protection on the inside with a thermal well. We've got protection that's required on the instrument side or the outside of the process. Inside, we've just talked about the thermal well, and we have to look at corrosion and erosion of the thermal well. And then the most important part of this would be the wake frequency and strength requirements. And we'll get into more detail as we go along here. But the wake frequency and strength calculations are very important when a thermal well is used in a flow that's going fast enough to cause some vibration of the well. On the outside, we said we had an explosive gas, so we're going to have to look at an assembly that is rated for those types of atmospheres. And then finally, how do we maintain this probe? What's the easiest way to be able to pull it out to calibrate or replace? and still maintain all of the hazardous environment ratings. And Jeff, I don't know if we have any questions so far.
Nothing at this point, but did just want to remind everyone that if you do have a question or you need some clarification on something, do go ahead and type it into the chat box or the Q&A section on your screen, and we'll go ahead and address that as we go along.
So when we're selecting a thermal well, we got quite a few things that we need to look at here. Again, now the wake frequency is going to be one of the more important things, and we have to look at, how are we going to attach it to the piping, pressure rating, temperature, and then is there going to be any corrosion, erosion? Is the pipeline vibrating? Things like that. So in our process, what we have is just water, so we really don't have to be too concerned about corrosion or erosion of the thermal well, and the wake frequency and strength calculations are going to take care of our issues with drag on the thermal well due to the flow rate, and then of course the pressure and temperature. Typically, temperature is not too much of a concern for a thermal well where an RTD is being used, because the RTDs are, they'll go up to about 500 degrees C is a typical industrial grade temperature limit for an RTD, and usually any of the stainless steels or even carbon steel is just fine at those temperatures. So there's a lot of different process connections, and I've shown just a few here. There's different types of weld-in sensors, ANSI style flanges, sanitary flanges, and even this one down here is a typically used in like a bioreactor. There's just a little O-ring seal on it and a backing nut that holds it all together. This is another type, I believe this is a European, I don't recall the name right off the top of my head. Jeff, help me out if you remember. No,
I do not. I apologize.
Okay. Anyway, but there's just a lot of different styles of process connections that are available with thermal wells. And if we had a corrosive product in here, there's also tables that will help us pick the right material. And this is just a little excerpt from one of those with just some different types of chemicals and things that where we've come up with the best option of materials for those. All the ones on here are all kind of metallics, but there are several plastics that work okay. Teflon comes to mind as one that works well for acids, and the price is not way out of line like maybe some form of Hastelloy or something that can also be used in acids, but it does erode or corrode over time. If we had a process where there was some erosion going on, there are some solutions for that. What we can do with the thermal well is actually coat it with hard-facing materials like stellite, tungsten carbide, or alumina, and those materials can make it last much, much longer. We had an interesting case a while back where a company that makes the kind of the grit or the gravel that goes on asphalt shingles, part of the process is they're blowing this through a pipeline, and it goes past a thermal well that has a thermocouple in it, and they pulled the thermal well out and the probe because they were getting some intermittent temperature readings, and they found that about half of the thermal well and most of the thermocouple had been completely sandblasted away. What was surprising is that as the thermocouple was being sandblasted, the two conductors in there actually kept touching each other, which is why they kept getting a temperature measurement, but about half of it was gone. And what we did with that one was put in a thermal well that had the stellite coating on it, which lengthened the lifetime by quite a bit, and then they just put a time frame on for replacement of that thermal well probe. So that turned out to be a good solution for that particular customer. Now the wake frequency issue, when you have a cylindrical object in a high flow rate, this turbulence can form on the downstream side of the cylindrical object. In this case, it's a thermal well. And if that oscillation of that turbulence matches the resonant frequency of the thermal well can start to vibrate. And so this is going to typically happen at some pretty high flow rates, depending on the style of thermal well. And this table shows where that can happen. If we have a 1/4 inch diameter temperature probe installed in the process, we can see it's roughly maybe 25 or 30 feet per second is where that probe at 4-inch immersion, that's this number right here, it'll start vibrating. And when it starts to vibrate, bad things happen. The probe can start to shift. The sensing element could actually go open circuit. And if it stays in there long enough, the probe could actually break off and go downstream and end up in, it's never a good place. Now, when we add a thermal well at that same 4-inch immersion, and this is one that's got a 3/4 NPT process connection on it, so the stem would start out at a 7/8 inch diameter, and they typically taper down to about 5/8. So that bumps up the safe flow velocity to about 250 feet per second. So it makes quite a bit of difference, and then going up in size increases it even more. So we get up here to a really larger size, and we're between we're roughly 550 feet per second. So that's something to certainly be aware of, and I always recommend that a wake frequency and strength calculation be done on the thermal well, especially if it's a new installation, just to be sure that it's suitable for that particular process. Now we move to the outside of the pipe where we have the explosive gas present. So we're going to look at connection heads and the different types of extensions that can be used between the thermal well and the connection head, and just a brief discussion of some of the agency approvals that are available for explosion-proof ratings. So the purpose of the connection head is to either house a transmitter or a terminal block, so we've got some place to land the wires from the RTD. It also protects it from moisture, damage from other dust and whatever else might be going on within the factory. And there's just a whole variety of heads that are available. Some are explosion proof. Different materials are aluminum, plastic, stainless steel, and different coatings. We show some here, like this one's got an epoxy paint on it. It's typically, it can be specified for pharmaceutical applications or food beverage where they're doing some wash down with caustic soaps and things, and it stands up to that kind of an environment and usage. Like I mentioned that it's a good place to mount the transmitter. Some of these are available with a indicator, and a few have actually a transmitter and indicator integrated right inside the same connection head. And what we need for our application is one that's approved for hazardous gas environments, which for this one we're going to choose a factory mutual This is a Class 1, Division 1, and this connection head actually covers groups A, B, C, and D. Now, one thing to be aware of when you're selecting a temperature assembly for a hazardous environment is that you want to make sure that the whole assembly is rated and not just the connection head. This head, and I don't think I guess we can't see it on here, but it has the connection head part number on the other part of the label, and it says that it's, enclosure only, and this is the rating on it. The assembly with this head on it will have another tag on it that has the actual rating for the complete assembly, because you can use a head that has a higher rating on it on a lower rated temperature assembly. I hope that makes sense. It can get very confusing, and I'm just looking at Factory Mutual. There are others. There's ATEX, there's IEC, there's the Canadian Standards, CSA, and they'll have a little different rating scheme, it seems, and we can certainly help out if anybody has specific questions about that kind of installation. Next thing to look at is the extension between the thermal well and the connection head. One of the more simple ones is just a straight pipe nipple. Some of the probes will require a coupling because the probe will have a male thread on it versus just going from the female threads on a well to female on a connection head. The one that I like the best is the one that includes a pipe union. It makes removing and installing the sensor much easier, in that you can orientate the connection head conduit connection any direction that you need just by loosening that union, and you can just rotate it easily and then tighten it up to lock it in place. When it comes time to calibrate the probe or to replace it, you can just take that union apart and pull the sensor out of the well and stick it in a dry block calibrator and go ahead and calibrate it that way. So it's really the most universal of these, and it's the one that I always recommend. So we have, so far we've got our assembly with our Explosionproof FM connection head on it. We've got the union extension, so we've taken care of some of the maintenance issues. One of the other things, having the head extended away from the process, it ensures that if you had a transmitter in there, for example, that it's not going to heat up past the service temperature of the transmitter. Most of the electronics in transmitters are limited about 80 or 85 degrees C, so that it is a bit of a concern, especially if you have a really hot process running. So the next category here is performance, and I'm assuming, Jeff, you're going to interrupt me?
Yeah, so I mean, just kind of a question. You talked a couple times about insulation, in particular with the surface mount sensor. So what do you recommend for insulation, or what are the different ways that you could insulate a sensor?
There are several different types. There's just the simplest one that we're probably most familiar with is just fiberglass insulation, and then there's some people are probably very familiar with some of the insulation that's made specifically for piping, and it'll have like a plastic coating over the top of it. There's some ceramic fiber type stuff for really hot type installations. And then even the expandable foam in a can can even be used for certain installations. So pretty much anything that works with your process is suitable to put over the RTD. Most of them are completely sealed up, and so if you do use spray foam over the top, it's not going to hurt the sensor any. The next section here is going to be on just looking at the performance of the sensor as it's installed in the process. So we've got two different categories here, the sensor accuracy and the actual measurement accuracy. And they can be quite different based on how the sensor is installed in the process. The RTD probes are generally very accurate. You can get it right out of the box with like plus or minus 0.13 degrees C at 0. And then you might stick it in a process that's got some problems, and you may end up with plus or minus 5 degrees as your measurement accuracy. So we're going to look at where those errors come from, how to minimize them, and how to get within our 1 degree Fahrenheit budget that we set at the beginning of this presentation. First thing to look at is what's called the interchangeability of the probe. And what this is just the tolerance band that the manufacturers use when they make a platinum resistance thermometer. So there are some equations that are used to calculate this interchangeability number, and these can be used at any given temperature. And in our example here, we may start out with this class B sensor from this standard, and this is the equation that's used. So we take the absolute value of the temperature. In our case, it was 150 Fahrenheit is where we're going to be measuring. Multiply that by we actually have to convert it to degrees C because all these equations and all the standards are all in degrees C. So we do that to get that interchangeability number at that temperature. Some of these have like a lookup table for the interchangeability. And there's also a graph available that you can look at to get that number. One of the big performance factors to look at, so we've got our interchangeability, and now we're looking at some of the installation errors here. So we have what's called, what we call stem conduction. It's also maybe ambient temperature effects. And what happens here is that the outside portions of the sensor assembly, in our case, since we have a higher temperature fluid than the ambient conditions, the ambient conditions have a cooling effect, a little chilling effect on that sensing element. And it comes down through the thermal well and the piping, and it also comes through the lead wires that attach the sensor to the outside world. And the only way really to overcome a lot of this is to have sufficient immersion length to minimize that effect. But in our installation, we have a 4-inch pipe, and so we can really only get the 2.5-inch immersion thermal well in there. And so we're going to have some kind of a stem conduction error. And with that, our example here, if we were to look at something like this with a 2.5-inch immersion, and it's 200 degrees C in the process and 25 C for ambient, here we'd probably have, maybe like a 3 degrees C error. And it's just kind of a guess, but that could very easily be the reality. And so that kind of makes our initial, 0.3 degrees C temperature probe just look very inaccurate. So when we have like a direct immersion style sensor to overcome this stem conduction, we like to have 10 times the probe diameter plus the sensitive length. That ends up being about 3.5 inches. Most of the sensing elements are about 1 inch long, 1/4 inch diameter probe, and just go through the math there, we end up with 3.5 inches. And that we found is a good rule of thumb. It doesn't work for everything, but for most liquids it will work okay. For air temperature, you typically would need more immersion, and I'm guessing it is probably even twice that would be necessary to really get away from all of these stem conduction. Now, for our application, we're using a probe and a thermal well. And this is a graph that we constructed based off of some testing, and we're getting about 1.6 degrees Fahrenheit just due to that short 2.5-inch immersion that we have in our example process. And if we look down here, we can see that we've got, we get down about 4 inches is where most of it goes away. It can maybe even go a little bit shorter on a thermal well like this, but usually about 4 inches will pretty much eliminate the stem conduction in most fluids. We want to make sure that we have a good accurate measurement too, just because it costs a lot if we're heating too much, not enough. It adds up very quickly. It's our example here. We're just using probably some older energy costs of 8.7 cents. Jeff, I think you found the new rate just today?
Yeah, I looked up the new rate, and I think the average kilowatt per hour in the U.S. for commercial is about 10.6 cents an hour, and it goes anywhere from a low of 7 or 8 down in Arkansas up to 25 or 26 cents up in Alaska. So it can be quite a difference and quite an amount of savings if you have to overheat something. You're putting too much energy into it.
Yeah, or on the other hand, if you're not heating it enough and you end up with bad product, that can cost a lot too. The bottom line, though, is that it really pays to get the most accurate temperature measurement that you possibly can for the process. Now, we've got already that 1.6 degrees Fahrenheit error, plus we've got our sensor interchangeability number. So we're already way over our little budget, and then we're going to be putting a transmitter in here too. So typically what we have as another rule of thumb is if you have more than 250 feet between the measurement point and a transmitter or your temperature controller or whatever it may be, it's a good idea to put a transmitter back at the temperature measurement point and just be sending that 4 to 20 milliamp signal or a voltage signal or whatever it might be, digital. It eliminates some potential errors with lead wires and things, and electrical noise, those kinds of things. There's radio frequency and electromagnetic interference can mess up a RTD resistance measurement that a signal conditioner may be doing. It also allows us to do what we call matching between the temperature probe and the transmitter. And that is one way that we're going to improve the accuracy of our measurement. So by adding this transmitter into the loop, we can actually cut out a lot of the interchangeability number. So what happens is that we will calibrate the temperature probe, and a typical uncertainty for that calibration would be like plus or minus 0.025 degrees C. So rather than having our bigger interchangeability number, we just have 0.025 C to put in that error calculation. And then we have we still have our 1.6 degree Fahrenheit error to look at for stem conduction. And most of that can be eliminated by wrapping this pipe in insulation. So our matching calculation, we you'll end up with about plus or minus 0.2 degrees C by looking at the uncertainty of the calibration that was done to the probe, the performance of the transmitter, and if you mix all those together, we end up with about plus or minus 0.2 degrees C. Roughly 0.4 degrees F. And we wrap this pipe with insulation. We can get down below that 1 degree Fahrenheit budget. And sometimes it's not even the pipe. I've had people actually extend it up to cover most of the extension, and in some cases where it's a more compact installation, they'll just cover the connection head and everything, and that eliminates most of that stem conduction error. And so getting into the price of this installation, as we saw that a bad, inaccurate temperature measurement can be very costly. Usually the initial cost of the sensor is one of the very smallest things that there is. We have to look at all of the not only that energy usage, but the maintenance costs. If it is a poorly designed sensor or poorly installed, if we had some vibration going on in our pipeline here, the thing might vibrate and fail prematurely, so we got to go in there and replace it, which, we got a lot of downtime, a lot of troubleshooting. You may lose some of your product, and then we've got spare parts that have to keep in stock or try to source those. And generally, it's always you need it in a hurry if it fails unexpectedly. So those are just some of the life cycle costs that you have to look at when you're choosing the sensor and how to install it in the process to get your best service life out of it. Take care of things really well. We're showing the USS Constitution here, old Ironsides. It's still afloat. They do a lot of maintenance on it. They upkeep. It's still going. The same thing holds true for temperature sensors. It's not typically just install it and forget about it. You do need to go back and calibrate it every once in a while, make sure that it's still doing what it's supposed to be doing. And looking at all the protection on the instrument side and also on the process side helps lengthen the service life of that component. And I think with that, if we have any questions, this is our final selection here. And the only thing I'm not showing is the insulation around the pipe. But I think this gives us the good accurate temperature measurement. We can maintain it easily. The thermal well is going to last a long time. We've chosen an immersion depth that's not ideal, but we were able to make it work okay with the addition of the insulation around this section of the piping. And that's going to be a pretty good selection for what we're doing here.
Okay, thank you, Bill. And just again, a reminder: if you do have any questions, go ahead and type them into the chat or the Q&A section, and we'll address them right now. Do want to thank Bill for the presentation, and also just kind of share with you, what we try to do in these sessions is to give you an idea of the things that you need to be aware of, the things you need to look out for in order for you to get the very best temperature measurement that you can. Our job is to help you do that. So if you have questions, Bill talked about there's some formulas here, there's air budgets, there's things of that nature. You're not in this alone. You certainly can give us a call, and we can help walk you through. But what we try to help people understand is you can take a temperature sensor and you can put it into the process, and most people think, okay, well, now I'm getting a temperature. Now I'm getting the temperature. What you're actually getting is a reading. And the real question is it a valid reading? Is it an accurate reading? And so the things that we kind of went through today kind of are those questions that you need to be asking yourself, or you need to help us, or you can call us and we can help you get through those questions to say, okay, yes, this is a good, accurate measurement. It's a lot of things that people don't think about, but because we deal with it every day, we're always thinking about it. So, if you do have questions, don't hesitate to give us a call. A couple questions that have come up from some folks on the session is, what is the temperature compensation factor for the thermal well?
Well, not exactly sure what that is referring to, but I would guess that we're just looking at, probably an error due to the immersion lengths, and it varies a lot based on the flow rate and the material that's in the piping, and actually the material of the thermal well can be a factor there, and also the ambient conditions. Stem conduction can be affected by things like a fan blowing on the outside of the temperature measurement point. The sun shining on it is another source of error. There's just a lot of things like that. I think that's what that question is referring to.
I guess the only other thing I can essentially a thermal well will heat up to the temperature of the process that it's in. Over time, there may be a time response issue where it's going to take longer for that thermal well to heat up and cool down than it would just the sensor itself. But eventually, it will get to the same temperature. And if you have sufficient immersion, then you don't have to worry about what's happening on the outside of the process. As long as you're far enough into the process, the impact is so small that it's not going to be noticed. Hopefully that answers your question. If it doesn't, feel free to send us an email, and we'll try to get you what you're looking for. Another question is, what's the typical cost for a calibration?
Yeah, now that's gonna vary a little bit. It goes anywhere from, like, if you just want to 0 degrees C, it might be I don't know, what is it, $10 or $15 item, on up to over $600 for a system calibration where we're doing a below to above zero calibration on a temperature probe and matching it to a readout. So there's various levels in between there. So like I said, it could just vary quite a bit. So and those are we can certainly help you out with, if you have something specific in mind, we can certainly address that.
Okay. And another question, is there any merit to using a less thermally conductive head, for example, a plastic versus metal head, when looking at the accuracy and stem conduction error?
Yes, it does make a little bit of a difference. I think the majority of the conduction error that we see happens on the lead wires, but all of the rest of it does make a difference. And things that are less thermally conductive certainly help minimize stem conduction. We've even used like PVC or other plastic extensions rather than having those out of galvanized steel or stainless. Stainless actually is not a very good conductor of heat, but plastic is even less of a conductor, so it would certainly make a difference.
Okay, another question here. Is there such a thing as a smart sensor, i.e. a sensor that not only sends a temperature reading, but also monitoring of the health of the sensor?
I do believe there is. I don't have any specific manufacturer names or anything, but I have seen that and read about it, and I don't know how well they work. I really, I don't run into that very much, but kind of the predictive maintenance thing would be, certainly is a topic that is discussed.
Yep.
Jeff, I don't know if you know anything.
Yeah, there are some products out there that kind of I guess are calling themselves smart sensors along the lines as to this question. Really, the sensor itself isn't what is smart. It's the electronics that you put on top of the sensor. So for the most part, the sensor does what it does, and usually it's in the transmitter, or there's some additional electronics that are built into, essentially on the, let's say, the top of the sensor, similar to a transmitter where it's doing some type of compensation or it's doing some type of comparison. In some cases, you may have two elements down in the sensor, and it's continually monitoring one element while the other element is doing the measurement. And if there's an offset of the two, then it gives you an alarm, something that says, hey, go ahead and check this. In our usually, I guess in our experience, what it's been is if you do some basic maintenance checks on your sensors and you are doing some calibration and you pay attention, what's happening over time. That's a better predictor than trying to put something in place. Because there's so many conditions, and it can only monitor so many conditions. But there are some out there that a little bit of an additional fail-safe helps to alert you in case you're not doing regular maintenance or calibration of your sensors. All right. Doesn't look like we have any other questions. If we missed on something, by all means send us an email and give us some more details, and we'll be happy to answer those questions. Or if you happen to think of something in the future, do go ahead and give us a call or shoot us an email. We do have a couple of RTDology sessions coming up scheduled throughout the year. Our next one is on wireless temperature measurement and trying to determine if it's the right fit for you. A lot of people are talking about it, but what does it really mean, and is it a good fit for what you're trying to do? And then in September, we have a session on how to identify RTDs, thermocouples, and thermal wells. And so, go ahead. You can go to rtdology.com, get some more information on those sessions. You can, as I mentioned earlier, you can also go to our YouTube page, search RTDology, and you'll see all of our sessions pop up, as well as some other videos on some specific topics. In the meantime, we're here to help. So if you do run into something or you've got a question, by all means, go ahead and give us a call. So with that, thank you very much. Have a good day, and we'll see you next time.